Hello, everyone. Today, we'll look at the technical overview of the SynC algorithm. The SynC algorithm is what we use to generate our synthetic society dataset, and this is a key piece of innovation of Arima. Today, we'll talk about the mathematics behind the algorithm, how it's created, how it works, why do we use it, and all the details that we need to know. All right, so let's get started. The problem with consumer data. As you know, the synthetic society is a data set of consumer behavior. And when we say consumer data, we're talking about all data sets that tell us about behaviors of consumers. So things like demography, socioeconomics, financials, healthcare, media consumption, all of that. Consumer data is important because it tells you a lot about who your customers are, what do they do, where do they live, work, and play, and it gives brands a lot of information and a lot of key insights. Now, common examples of consumer data include things like census, market research panels, CRM databases, card transaction mobility data, and so on. And because it's information about people, it often comes with privacy challenges. So we'll look at two main forms of consumer data, aggregated and respondent level. Each has its pros and cons, both with respect to usability as well as privacy. And we'll look at how we work with both datasets. So let's start off with looking at aggregated dataset. When we say a dataset is aggregated, what we're referring to is how the dataset is being recorded. So here you can see in this slide, I've given an example. We have postal codes, and we have different postal codes. And let's look at the first one, A1A1A1. In this postal code, there are 53 people. We know 12.3% of them are between 30 to 34, 18.5% are between 50 to 59, and so on and so forth. Similarly, for the next postal code, we know how many people are there, and we know how many people fall, what percentage of them fall within each bucket. Datasets are aggregated when there are many individuals that are averaged into one particular aggregation unit. And here, obviously, postal code is the aggregation unit. Commonly, geographies have been used for aggregating units. Postal codes, census blocks, these are just some examples. Because of the census, aggregated data are generally have very good coverage. They're available at the national level. However, key information is lost as a result of aggregating data. So for example, if you look at the first postal code, we know about half of them own dogs, but we don't know who they are. So if you were to ask how many people own dogs and watch CNN, we can't answer that because the information is lost through aggregation. Then you have something called the respondent level data. Respondent level datasets are datasets where every individual is one record, as opposed to the example before where every geography of many people are preserved as one record. So here we have IDs 1, 2, 3, 4. Postal code, we know exactly where they live. This person is 30 to 34, and we know each of the values they've answered for every one of these questions. Respondent level datasets generally include more details. They have more details about how individuals are different, what questions they've answered. But at the same time, individual level data, because of privacy challenges, they generally don't come with an identifier, so no personally identifiable information is included. You won't be able to match that against other data sources, and they're also generally limited in size. So they're not usually it's a market research data set, which is a subset of the population, or they may come from your CRM database, which is again a subset of the population, and you won't have 100% of the true population. So the ideal scenario is one where we have the best of both worlds. We have a population data set with granularity, so individual level, respondent level data, and at the same time, they have the representation of a national level data set, like the aggregated data set, and they, of course, uses no PII. And that's what synthetic populations do. So a synthetic population It's a statistical reconstruction of the true population when the underlying data sources are either less granular, like the aggregated case, or less representative, like the respondent level case, or both. Somehow we should be able to train up a model so that the model can statistically generate the true population given these imperfect input data sources, and that process should not depend on matching data. So we don't need the data set to have names or emails or anything for us to match against. It's simply done in a statistical way. So the SynC algorithm is something that we've developed here at Arima. It's a generative AI algorithm that automates the process of building population level dataset from aggregated and responded data sources. The algorithm relies on the three key assumptions. One, original data is preserved as much as possible. So it's not a process that necessarily invents new data set. The data set that we create is constrained by what's being inputted. So it needs to look as much as possible. It needs to look like the information that's been given. Second, this process can be done with as many sources as needed without using PII. So whether it be 2 sources, 5, 10, 20, 50, 100, it should be able to take on as many data sources as needed, and we're not matching any keys among these different data sources. So we don't require any of them to have common keys like age, like names, email, phone numbers, address, none of that for matching. Finally, the population size can be arbitrarily large. This is generally a computational consideration. If your population is really large with a lot of variables, your algorithm need to be able to work as well. It can't take too long computationally to generate that population. As the finished product, the synthetic population is a data frame with n synthetic individuals, each with m attributes. So n is the national population, meaning that if we're generating a synthetic population for Canada, n needs to be 40 million because we have 40 million people in Canada. If we're generating a synthetic population data set for the US, we need 325 million because that's how many people are in the US. M is the total number of attributes across all sources. So for example, source 1 has 10 variables, source 2 has 50, source 3 has 100. Then in our finished product, we need to have all of these variables. Synthetic individuals are anonymous and they're attached to the lowest level of geography in their country. What that means is if the lowest level of geography is the postal code, for example, in our previous example, then every synthetic individual we generate are attached to that postal code. Beyond the postal code, they're anonymous, so you don't go into the postal code and try to identify who is who, but rather they're statistical creations of personas that mimic people who live in the postal code. Every person has a value assigned for every attribute, so across our M attributes, everybody needs to have all M attributes, even if the original sources don't include them. So even if our original data sources aren't complete, there are missing values, there are some people that are not being sampled, there are underrepresented groups, whatever. In our finished product, every person needs to have every attribute, so it needs to be a complete data set with no missing values. Here are some additional data sources that are additional academic sources that we published over the years, which you could look at if you're interested. And now let's take a look at how such a data set is being generated. We'll start with the first example of working with aggregated data set. So suppose that we have a postal code that looks like this. We have 3 people in that postal code. We know one is between the age 25 to 29. One of them is between the age 35 to 39, and one is between 60 to 64. In terms of profession, we know one is a construction worker, one is in IT, and one is in healthcare. We also know their education and marital status. So the question is, how can we generate 3 synthetic individuals because there are 3 people in this postal code based on the information given. If you look down on the chart on the bottom, essentially we're looking at filling out that chart. Think of it like a little bit like a Sudoku puzzle. We have some constraints that we must follow, and we're trying to fill out all the missing values. Because we have 3 people, we'll name them 001, 002, and 003. Those are the IDs that we'll give them. We'll start with assigning an age for every person. And because at this point we know nothing about them, we might as well just randomly assign an age to somebody. So we'll say the first person is 25, the second person is 35, and the third person is 60. Now, once we have our first value assigned, we can now iteratively assign the next set of values based on conditional probability. The next value in line is profession, so we can now calculate the conditional probability of age given profession. In other words, when we assign age, we know nothing about that person, so we can't do any better than just randomly assigning. However, once we know someone's age, what we're saying is now that we know their age, we can say more about what that person's profession is than just randomly guessing. So once we have a little bit of information, we can try to better assign the next value than randomly guessing. And once we have 2 values, age and profession, we can now say a little bit more about the person's education. So we're going to, again, use conditional probabilities to figure that out. And as we know more and more about a person's more and more attributes, we can assign these values better and better. And now, of course, order matters. So why do we start with age and not profession or marital status? Well, that is a very important question. We can either use an algorithm to select the right order, such as forward selection or backward selection, or we can also just use our intuition and start off with the more important variables and followed by the less important variables. All right, now let's look at dependency modeling. To predict the probability of a variable given another variable, we train a model on the aggregated data set and extract correlation patterns to use that in the individuals. One of the assumptions we're making here is that if 2 things correlate at the postal code level, then they'll also correlate at the individual level. For example, if we see that for postal codes with higher income, if we also see a higher proportion of them traveling to Europe next year, for example, if we see a positive correlation between income and traveling, then we'll say at the individual level, such correlations also exist. So in other words, for individuals, if this is true at the postal code level or at the aggregated level, then at the individual level, those who have more money will also have a higher tendency to travel. So using aggregated data, we can compute the probability of profession given someone's age. So here you can see we're lining up these values. So for every one of these postal codes, we know how many people fall within each of the age buckets. That's the distribution of age. And we use that to predict how many people would have fallen under each of the profession buckets. One thing we should realize is that individuals are nothing more than a 1-person postal code. So once we've developed our model and have the model learned correlation patterns for age and profession, we can now turn our attention to individuals. There are 3 individuals that we're interested in modeling. We can pretend that there are 3 1-person postal codes. We've one-hot encoded them so that our first postal code has 1 person, which is first postal code is also our first individual, has 1 person. 100% of that populated postal code is between 20 to 25 to 29 because there's obviously only 1 person. In our second postal code, which is also just 1 person, 100% of that postal code is between 30 to 35 to 39. And when we have one-hot encoded all of our individuals, we can now ask our model to make a prediction. So our model makes a prediction and says that for the first person, there's a 40% chance that they're in construction, 35% chance that they're in IT, and 25% chance that they're in healthcare. And for the other individuals, the model has also made its predictions. Now, once these values predictions are done, and our job is to then assign somebody a rank. Now, remember, when the model makes a prediction, it gives you a probability. But for a person, you can't have a probabilistic profession. You can only take on one value. So you're either in profession, or you're in IT, or you're in healthcare. You can't be in all three. So how do we assign that value? Well, we do so by looking at probabilities and ranks. Probability tells you how likely you are to be in a profession relative to your other professions. And rank tells you how likely you are going to be in a profession relative to your neighbors. So let's look at person one. Person one has a 40% chance of being in construction. That probability is higher than every other profession out there. At the same time, person one has a 40% chance of being in construction, and that's also more probable than all of his neighbors. So in this case, we say person one being a construction worker is a clear winner, meaning that's more likely than every other possibility, and that's also more likely than everybody else. So we could say person one is our construction worker. And because one person can only have one value, once you get assigned a profession, you're essentially out. So we don't have to consider person one anymore. Similarly, because the census tells us that in this region, there's only one construction worker, now that value has been taken, we also don't have to consider construction workers anymore. So let's look at person two. Person two, it's a tie for IT and healthcare. But that's okay. We can skip that person for now, and we'll go to the third person. For similar reasons, the third person is a clear winner in healthcare, and that takes up that value. So all that remains is for person two to be the IT profession. Similarly, we can complete education and marital status. If we know there's only one university grad, I'm sure most of you would agree with assigning that to the construction worker, and IT and healthcare being the university grad. And same thing, you can assign the person's marital status as well. And now we would have completed our table, and we have generated a 3-people synthetic population based on the given information. Now, this process ensures that one, you get assigned the most likely outcome among all outcomes. So if you have 10 different possible professions, you get the higher the probability is, the more likely you're going to get assigned that value. Also, the more probable person in the region gets assigned. So if you're more likely to be in a profession than your neighbors, then you will get assigned that value. The number of assignees match the given regional total. So if the census tells us that in this neighborhood there's one construction worker, then exactly one person needs to be assigned that value. And lastly, multiple data sources can be joined by geography. Here, there's no reason why age, profession, education, and marital status should come from one data source. They could come from multiple data sources, and you can join them by geography. There's no requirement of any of them coming from the same data source. So long as you have the geography, you can all join it together. Now, let's look at the second example. In the second example, we're synthesizing micro-level data. In other words, we're synthesizing individual respondent level data. To do so, we need to start with a population. So we'll assume that we use the population from the previous example. So our 3 guys, the construction worker, the IT and healthcare professionals, they're now back again. Typically, microdata contain specific variables about a particular sector or brand. These data sets are usually commissioned by a market research firm, or they may come from a CRM database from a company. So they're generally very domain specific. Like in this case, we have three variables from a travel study. The questions are: have you traveled to Europe last year? Are you planning to travel to Europe next year? Is it a business trip or not? That said, in most cases, most of these individual data sets also have generic variables. Like in this case, we have age and marital status. Age and marital status here are found in this data set that we're trying to synthesize, as well as our population. So we call these our common keys. Common keys are not always identical. In this case, age is slightly different, but we could do some simple data cleaning to align them. Geography, if they're available, can be common keys as well. So like before, once we have the common keys, we can now calculate the conditional probability of the new attributes given our common keys. So in this case, we're calculating three things: the probability of travel to Europe last year, given age and marital status, and travel to Europe next year, and business travel, and so on. One assumption we're making here is that the new attributes are conditionally independent, which means that the common keys we use are enough to explain all variabilities among the three new variables. With just age and marital status, this is probably not true, but generally speaking, our common keys are much larger. We're looking at a set of maybe 8 to 10 variables, including age, gender, profession, marital status, personal income, family income, and so on. So with a large set like that, you could, it's quite safe to assume that these variables are enough to explain all of the variabilities. So in other words, what we're assuming is that given these variables and given the common keys, the new attributes are conditionally independent. And you can validate that with R-squared or out of sample accuracy as well. Again, here you can use any classification algorithm you want to make these predictions. Once we have our model trained from the last step, now it's time to make the predictions. Like before, we make predictions for each of the individuals, and now we have a probability. If you remember from our previous example, once we had these probabilities, we then had to assign values based on ranks and probability. So in other words, we gave a value to someone if that value is bigger than all other alternative values, as well as if that person is the most probable within their neighborhood. Obviously, in the individual level data case, we don't have neighborhoods, we don't have aggregation units, so it's difficult to make such assignments, but we're going to use the same kind of idea. And instead, we're going to try to create cohorts not based on neighborhood, but based on age and gender pairs. So we're creating cohorts to compare one against others that are similar to that. So for example, we can create cohorts by putting all the 20 to 24-year-old male together, 20 to 24-year-old female together, and so on and so forth. Within each aggregation unit, again, we assign values based on ranks and probabilities, just like before. So for example, among all 20 to 24-year-old males, if we found that in our original data, let's say 10% of them plan to make business trips, then within our synthetic population data set of all the 20 to 24-year-old male we generate, we need to make sure the top 10% get values assigned to be likely to take a business trip next year. We do so to avoid the situation where everybody, let's say if we found that profession and taking business trips were highly correlated. If you didn't do that, then maybe all of the business management people take business classes and nobody else takes those trips, and that's probably not true. So having these cohorts and again comparing people against others in their cohort will make sure that everybody gets there's a good chance of that value being assigned more evenly as opposed to being assigned to everybody who fall under a particular bucket. Age and gender pairs doesn't have to be the only choice of cohort. You could also do it by income. You could do it by by state, or maybe by a mix of age and income and family, or whatever. We just found using age and gender pairs to be the easiest to work with. Once the individuals are synthesized, we're pretty much done with the process. One last thing I want to add is that this process of assigning individual level data does not require one to access the original data. Sometimes it's a real big challenge for a lot of organizations to share data. For example, share data with us to go through this process. You actually don't. All we need is the classification model, which can be trained locally on your machine, and also the cohort summary. In other words, all you have to do is tell us 20 to 24-year-old male, 10% of the people do this, 20 to 24-year-old female, 12% of them do this, and so on and so forth. Think of that as the sufficient statistic of the process. And once we have the model and the sufficient statistic, we're able to process the individuals. Not a problem. And last, and just a little quick summary of the SynC process. The SynC process produces what we call the maximum likelihood population rather than a perfect reconstruction. So in other words, the population we produce may not be identical to the true population, but it is certainly the most probable outcome we created based on the available data. Geography is a central key in this whole entire process. Without geography, we won't be able to make it happen. So geography is central, and the use of geography replaces the use of personally identifiable information. Order matters, and one should always start with the most general variables. So if you had a choice between starting with age and using age as an explainer for all other variables versus, let's say, the number of cups of coffee people drink and use that as a predictor for other variables, we'd want age to be the predictor. And lastly, the SynC process is one which is designed to extrapolate on collected data sets. So throughout the process, we're not necessarily inventing anything new, but rather we're simply generating a larger data set that's benchmarked against what we've given with. And it's a process of enlarging or extrapolating given information to make it to increase the sample size. And with that, we conclude this presentation. If you have any questions about synthetic data or how this process is generated, or if you'd like to see a sample of what we have, feel free to reach out and schedule time for a demo. Thank you.